Bismillahirrahmanirrahim. Assalamu alaikum. We will start with Naïve-based classifier. As the name suggests, Naïve-based classifier works on a principle of Bayesian learning framework. This classifier exploits Bayes' theorem to compute the probability of hypothesis being true given data. That is the principle in Bayesian learning framework. And the word naive is due to the one assumption we carry out in computing probabilities, and that assumption helps us in computing probabilities very efficiently. Before we carry out mathematical treatment of the topic, we will start with one simple example in which we will build naive-based classifier to have so that you can have a basic understanding of the concepts. Okay, we assume that we are given this data. We have information about on any particular day. We have information about outlook, temperature, humidity, and wind, and we want to carry out prediction whether there will be a play on that day or not. Right? And we are given this data for 14 consecutive days. We're given temperature, humidity, uh, outlook, and wind information, and we want to build a classifier that can help us in predicting the play, whether play is equal to yes or play is equal to no. Mathematically, it simply means we want to compute these two probabilities: probability that play is equal to yes given information about these four features, or play is equal to no given these four features. And for example, we will consider we want to carry out prediction for sunny outlook, high humidity, cool temperature, and weak wind. So this is our test point. We want to carry out prediction for when we have these values of the features, and we are given this data for the prediction. Our approach would be that we will compute these two probabilities and we will predict the most likely. Okay, let's see how do we compute these probabilities. So we want to compute probability when play is equal to yes given the values of the feature. In order to compute this probability, we use Bayes' theorem. And using Bayes' theorem, we know that probability of if this is A and this all is B given A given B is probability of B given A times probability of A divided by probability of B. In order to compute this probability, so this is a joint probability, right? So this term, probability of B, so this term is a joint probability of four random variables. One random variable is outlook, temperature, humidity, and wind. So this is a joint probability of four random variables. And if you want to compute this probability, we need these instances in our data set. But we have a very limited data set. How can we compute this probability? We carry out one assumption. We make one assumption to compute this probability. And that assumption is called naive assumption, due to which this classifier which we'll build is called naive-based classifier. This assumption states that features are mutually independent given the label. So they are mutually independent. That means every feature is independent from the other. As we said earlier, that mutual independence implies pairwise independence. Right? It simply means we can write this probability of when outlook is sunny, temperature is cool, and humidity is high, and wind is equal to strong, given play is equal to yes. I can write this as a product of four individual probabilities using or exploiting the independence between the features. Right? So I have expressed this in this form. Right? And now I can, if I can compute these probabilities, so this one, from the data, I can just multiply these four to get this probability, right? Okay, let's compute these four probabilities. Let's estimate these four probabilities from the data. So we have this data. So we have 9 instances in which play is equal to yes, and we have 5 instances in which play is equal to no. Right? If we want, given play is equal to yes, and given this data, we want to find out what is the probability outlook is equal to sunny given yes, given play is equal to yes. How do you compute this? How do you make an estimate of this given this data? We simply find out how many instances of sunny do we have. So we only have 1 and 2 instances out of 9 sunny. So we can say probability of outlook is equal to sunny given play is equal to yes would be 2 by 9. Similarly, probability when temperature is equal to cold given play is equal to yes, that would be, so we have, this is cool, this is cool, 2 and 3 instances, so 3 out of 9. So we're given play is equal to yes, so total would be 9, and out of 9, in 3 instances we have temperature is equal to cool. Similarly, probability of humidity is equal to high given play is equal to yes would be 3 over 9 as well. Probability of wind is equal to strong when play is equal to yes, this would be 1, 2, 3, 3 by 9 as well. And finally, what is the probability when play is equal to yes? We also need this because in Bayes' theorem, in numerator, we also require probability of play is equal to yes, that is 9 by 14. Let's also compute these probabilities given play is equal to no. So when play is equal to no, we have 5 instances. Out of these 5, we only have 2 and 3 sunny, so 3 by 5. Similarly, temperature is equal to cold 1 over 5, humidity is equal to high, given play is equal to no 4 by 5. Wind is equal to strong 3 by 5, and probability of play is equal to no is 1 minus 9 by 14 or 5 out of 14. We only have 5 instances out of 14 instances. So these are the estimates we could make from the data, right? Okay, let's substitute these numbers and we compute this term. So this is the numerator what we had in the Bayes theorem, right? So this is times this. So we want to find out probability of outlook is equal to sunny given play is equal to yes, temperature is equal to cool given play is equal to yes. These are the 4 features for which we want to carry out prediction, and we also multiply this with probability play is equal to yes. And when you compute this, it turns out to be 0.0053. We carry out the same for play is equal to no, and when we use these numbers, we obtain 0.0206. If you note here, I have not computed the denominator we had in the conditional probability expression, right? So this is the numerator only, because denominator is same in both the cases. We don't need to compute denominator, and also denominator does not depend on play is equal to yes or play is equal to no. It's independent of hypothesis we want to make. Okay. Given this, we can make a decision that play is equal to no is equal to more likely, because 0.0206 is greater than 0.0053. But if you want to find out denominator, you can find out. How? It will be a sum of these two, right? Right. So if we want to find out posterior probability of play is equal to yes, given these 4 features, that would be equal to what we had in the numerator divided by the sum of these two. This will be 0.2046, and for play is equal to no, we get 0.7954. So these two are simple scaled by, so scalar versions of 0.0053 and 0.006. And as you see here, 0.79454 is greater than 0.2046. So our prediction would be play is equal to no, because it is more likely, right? So this is all what naive Bayes classifier is. So we want to find out posterior probability. We exploit Bayes theorem to express posterior probability is equal to product of likelihood and prior, right? And we compute these two from the data we have. And while computing the likelihood, we made one assumption, naive assumption, that features are independent of each other. And this is a very uh, this is a very good assumption that helps us in computing these probabilities very quickly, very efficiently from less amount of data. And we will see more details about this in the next video when we mathematically formulate naive Bayes classifier. So we stop here and we'll continue in the next video. Thank you, Ji.